Hello everyone. Today we will start with the session 3 of hydrogen and its compound. Today we will mostly study about a new compound that is made from hydrogen atom, that is water. Basically hydrogen have its name because as explained in the session 1 also, that hydrogen means water generator, right? So that's how the name hydrogen came from. So students are requested to drop down their name for attendance purpose. Then we will start with the session. Students are requested to drop down their names for attendance purpose. We will start with the session. Okay, so we'll start now. See, particularly we will learn about water, its structure and its physical properties, right? So this particular topic is very important from this chapter, so pay attention to this session. See, human body, if you will see, it consists of 65% water, and plants, some plants basically have as much as 95% water, right? So basically, why is water important? Because it is a crucial compound for the survival of all the life forms that exist in the biosphere. Now, if you will look at particularly that what are the sources of water, we know that it is ocean, saline lakes, polar ice and glaciers, groundwater, lakes, soil moisture, atmospheric vapor, atmospheric water vapor and rivers, right? And beside this, we know that maximum amount of water comes from the ocean, right? About 97.33% of the total water that is available on the earth's surface is present in ocean, right? Now then it comes to the polar ice and glaciers on the second number, that means 2.04. And the least one will be particularly the rivers, that is 0.0001. That means how much? 10 raised to the power minus 4 approximately, right? So why is water important? Particularly because it is a crucial compound for all the living organisms which are living in the biosphere itself. Now next, to consider the structure of water molecule. Already we have discussed this in chemical bonding in detail, so we will just have a gist of it now. So we know particularly that oxygen here is what? sp3 hybridized according to the hybridization theory, and we know that two lone pairs are present. It is having tetrahedral geometry. And what is the shape of water? Particularly the shape is bent shape or V shape. You can also say bent shape is more accurate, right? So here if you will see what happens, that the ideal tetrahedral angle is somewhat around 109 degree, right? But here you will see that there is a decrease in the bond angle of HOH than that of the ideal tetrahedral angle. So why is this so? Because of the lone pair repulsions, right? This all we have covered in chemical bonding in detail. So for now we need to learn that particularly the OH bond has a bond length of 95.7 picometer and the angle is differing from the ideal tetrahedral angle. That means the angle is less than that of the ideal tetrahedral angle, that is 104.5 degree. Now you come on to the dipole moment. So dipole moment, if you will particularly find out, we find out on the basis of the electronegativity difference, right? So here we know that the dipole moment due to the lone pair will be somewhat like this. Here also it will be somewhat like this, and for the OH bond particularly, we know that electronegativity of oxygen is greater than that of the hydrogen. So the dipole moment will be somewhat like this. So the resultant dipole moment will come out to be like this, right? They all will add up and the resultant dipole moment will be this. That means the water molecule is polar in nature. And what is the magnitude of the dipole moment? 1.82 dBi. Right? So water molecules are polar in nature. In liquid phase particularly, they are held together, basically the water molecules are held together by the hydrogen bonds. We know that when does the hydrogen bonding takes place, there are two conditions. First, there should be a hydrogen that should be attached to a electronegative atom or element. Right, so here you can see that in water, oxygen is electronegative in nature and which is attached to the hydrogen itself. So it will show hydrogen bonding, which is denoted by dash here, right? Basically what happens, that water molecule is like this. So here partial negative charge and here partial positive charge, right? So this particular hydrogen bearing a partial positive charge is attracted by the oxygen of the next water molecules, and the type of interaction that will be there is the hydrogen bonding. So hydrogen bonding is nothing but a particular or a special type of dipole-dipole interaction. Due to this extensive hydrogen bonding, because oxygen is much more electronegative in nature, particularly you can remember the electronegativity order as FON, that means fluorine, the highest electronegative element, then oxygen and then nitrogen, right? So because of this hydrogen bonding, this also leads to the formation of water in the solid state that we known as ice, right? So also it has high freezing point, high boiling point, high heat of vaporization and high heat of fusion in comparison to H2S and H2SC. See, actually what happens, we will learn this in 12th class also particularly. We will just have an idea for now. What happens that as the molecular mass increases, boiling point also increases. Boiling point also increases. That means if I compare H2O, H2S, H2SE and so on, so what happens here, that the atomic radius or the atomic mass also increases down the group. So boiling point basically should increase. But what happens here is, amongst these three, water is having the highest boiling point. Why is this so? Right, in spite of having a lower atomic mass, it is having a greater boiling point. This is due to the hydrogen bonding, which is absent, or basically it is less in case of H2S and H2SE. Why? Because they are less electronegative than oxygen. Less electronegative than oxygen. So basically you can learn this, that greater the electronegativity of the central atom, or basically the element which is showing the hydrogen bonding to which the hydrogen is attached, it should be of greater electronegativity to have a pronounced hydrogen bonding. As the electronegativity decreases, the hydrogen bonding also decreases. The extent or the strength of hydrogen bonding also decreases. Right. So due to this additional hydrogen bonding character, water is having a high boiling point than that of H2S and H2SC, in spite of water having a low molecular mass. So this is a particular area of question that you can get here, that why water is having a high freezing point or high boiling point or high heat of vaporization or high heat of fusion in comparison to that of H2S and H2SC. Now this is very important. See, basically water is polar in nature, right? And we know that ionic compounds have greater polarity than that of covalent compounds, right? And we also know that like dissolves like. Like dissolves like. That means what? That polar molecule will be soluble in polar solvents, and non-polar molecule will be soluble in non-polar solvents, right? So particularly because the polar character is less in case of covalent compounds like alcohol or carbohydrates. What are carbohydrates? They are compounds made up of carbon, hydrogen and oxygen, right? And alcohol particularly are also made up of carbon, hydrogen and oxygen, right? So these are the elements which make alcohol, and same elements basically make carbohydrates. When we will study particularly organic chemistry in detail, then you will know that how particularly in spite of having the same elements, alcohol and carbohydrates differ, right? So for the meanwhile we can know that alcohol is having carbon, hydrogen and oxygen, and carbohydrate is also having carbon, hydrogen, oxygen, and they are covalent compounds. That means they should have low solubility in water, right? Because they are non-polar, or basically they are less polar than that of ionic compounds, so they should be insoluble in water. But due to hydrogen bonding, they are soluble in water, or they particularly dissolve in water. For example, sugar is a carbohydrate that dissolves in water, or the alcohol particularly is also soluble in water. That is due to hydrogen bonding. They should have been insoluble because they are less polar and water is more polar, and because like dissolves like, so what happens that polar should dissolve polar only, and non-polar compound should be soluble in water. But due to the hydrogen bonding, alcohol and carbohydrates like compound, they form hydrogen bonding with water molecules, and therefore they dissolve in water easily. Now the crystalline form of water is ice, right? So basically ice can have two forms. One is the hexagonal form and one is the cubic form. So particularly at high temperatures, if you will say, hexagonal form will exist, and at very low temperatures cubic form will exist, right? So this is a cage like structure of ice. You can see here that there are hollow spaces. There are hollow spaces, and we will also particularly learn this in the next slides, that due to this hollow spaces, hollow cage like structure, what happens, that density of ice is less than that of water, right? What happens generally, that solids have a greater density than that of liquids. They are more heavy than that of the liquids. But here what happens, that due to this hollow nature of the ice, cage like structure of the ice, density of ice is less than water. That is why it floats on water, right? Particularly we should know the principle that the lesser density compound will always float and the lower density will always remain at the bottom, right? So ice, that is why ice floats on water. Now X-ray diffraction studies, what are X-ray diffraction studies particularly? That they tell about the structure of a compound or an element particularly, right? For example, bond length you want to determine, or particularly you want to determine the structure of the compound, that what is the structure of water, let us say, right? So similarly, through X-ray diffraction, it is a technique that is used to determine the internal structure of any compound or any element particularly, right? So X-ray diffraction shows that each oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms, right? So here particularly you can see that oxygen, let us say this is oxygen, and it is surrounded by 4 other oxygens that are tetrahedrally arranged, right? So this is how particularly a water molecule exists in the form of ice. However, this is not important. This you should keep in mind particularly, that ice has a cage-like structure first. Second, ice has a lower density than that of water in spite of being a solid, and ice exists in two forms, that is in the hexagonal form and the cubic form. At high temperatures hexagonal form is favored, but at very low temperature it condenses to cubic form. Next, so basically this open cage like structure is due to the hydrogen bonding, and these holes are particularly wide. So any atom, we have talked about the interstitial compounds. Here also what will happen, that any compound which will fit the size of the hole particularly, or the cage particularly, will get inserted into these gaps, right? So basically due to the gaps in the structure, because of these spaces in the structure, ice has a less density than that of water. Density of ice is less than that of water. Okay. Next, so this already we have discussed that due to its less density, ice cube floats on water. Now the application of this is particularly thermal insulation of lakes. What happens here is that, see, let us say that this is a lake, right? And in winter season what happens, that because ice is having a less density than that of water, what happens here is that ice forms a shield on the surface. This particular surface becomes ice, right? And it prevents the water that is present below it to be formed into ice, because here what is happening, that aquatic animals or the marine animals are living, right? So here what happens, that ice acts as a thermal insulation, so that the water that is present below in the lake does not get converted into ice, and therefore it helps in the survival of the aquatic life, and this fact is of greater ecological significance, right? So basically it helps to maintain the ecosystem. This is an important application of ice, or important application of the fact that ice cube floats on water. Next, you consider the properties of water. We already know H2O. So hydrogen is what, 1U. Again, other hydrogen is 1U and oxygen is 16U. So the total mass becomes approximately equal to 18U or 18 gram per mole. Its melting point is very much important, that ice converts into liquid, or basically ice is in equilibrium with the liquid at 273 Kelvin. Right, so at 273 Kelvin, the ice starts melting into the liquid. Boiling point, the water converts into water vapor at 373 Kelvin, or we know it as 100 degrees Celsius, because here the temperatures are in Kelvin. Here also the melting point is 0 degrees Celsius. Right, and yeah, other things you don't need to remember, you can only remember these three things: molecular mass, melting point and boiling point. However, you can have a look of enthalpy of formation, it is minus 285.9 kilojoule per mole. Enthalpy of vaporization 40.66, enthalpy of fusion 6.01, temperature of maximum density 276.98. Now this is very important. This is an area of question, that at what temperature water has its maximum density. Now your work is to convert this particular Kelvin into degrees Celsius. Convert it and tell me the answer. Convert 276.98 into degrees Celsius and tell me. What should be the answer? How do you convert Kelvin into degrees Celsius? Calculate and let me know that 276.98 means how many degrees Celsius? Anyone? Convert this into degrees Celsius, 276.98. Anyone? Anyone? How do you convert Kelvin into degrees Celsius? Particularly, degree Celsius is Kelvin minus 273.15. Right. So you have to subtract 276.98. You have to subtract 273.15 from 276.98. That will give you the temperature in degrees Celsius. Right. So it will be approximately around 3.98 degrees Celsius. The conversion factors you should remember, that how do you convert degrees Celsius into Kelvin, how do you convert Fahrenheit into Celsius or Fahrenheit into Kelvin. So the answer should be 3.98 degrees Celsius. You have to just subtract 276.98 and 273.15. So the answer that you will be getting here is 3.98 degrees Celsius. So 3.98, or you can also remember it at 4 degrees Celsius, is the temperature of maximum density of water. That means the maximum density of water is at 4 degrees Celsius or 3.98. Density is 1 gram per centimeter cube. 1 gram per centimeter cube. So in comparison to other liquids, because water is a pure liquid, right? So it has, in comparison to other liquids, it is having high specific heat, high thermal conductivity and high surface tension. And also the high heat of vaporization and heat capacity are responsible for moderation of the climate and body temperature of living beings. So water also helps in maintaining our body temperature. This is very important. Another application of water, that it maintains our body temperature. Now viscosity is 0.89 centipoise. Basically we will learn the viscosity in the states of matter chapter. Dielectric constant is very much important, not the value, but you should learn that dielectric constant of water is very high, right? So because the dielectric constant of water is very high in comparison to other liquids, therefore it has the tendency to solubilize maximum number of compounds. Maximum number of compounds. That is why it is also known as what? It is also known as universal solvent. Universal solvent. We will, or the conductance of distilled water is very less, while the tap water, because of the presence of sodium, magnesium, calcium, salts and ions, it conducts electricity. So this you should remember, that the tap water conducts electricity. Why? Because it is having ions like sodium, magnesium and calcium. While distilled water, if you will take, it is having a much lower conductivity than that of the tap water, because of the absence of ions like sodium, magnesium and calcium. Yeah, so this we have already studied. Because of its dielectric constant, mostly ionic compounds dissolve in water, and that is why particularly it is known as the universal solvent, right? And also the solubility of covalent compounds. See, solubility of ionic compounds, you can say that polar interaction takes place. That means like dissolves like. So water is also polar and ionic compounds are also polar. So particularly they dissolve in water, because like dissolves like. But here the solubility of covalent compounds, as we have already discussed, is due to the hydrogen bonding with water, right? So solubility of covalent compounds can be explained in this way. So the question that can be asked from here is that why alcohol is soluble in water in spite of being a covalent compound, why amine is soluble in water in spite of being a covalent compound, why urea is soluble in water in spite of being a covalent compound. So you have to answer them that they form hydrogen bonding with water, and that is why they are soluble in water. Now you give the answer to this particular question. Answer this particular question. Deliquescent substances are usually insoluble in water, highly soluble in water, or slightly soluble in water. Okay, so Sarayus, okay, so then, okay. So they are highly soluble in water. Sudhain is right with his answer. So what are deliquescent substances particularly? Deliquescent substances are those substances which are highly soluble in water. That means they extract water from the solution in which they are dissolved, right? And more information, we will have a full study of this, that what are deliquescent, what are hygroscopic compounds and all in these slides only, in the next slides. So further, chemical properties of water. First is the amphoteric nature. So amphoteric nature, if you will say, what is amphoteric nature? That means it can behave as a base also and it can behave as acid also. That means if you take water with the acid, it will behave as a base, and if you will take water with a base, then it will behave as an acid. For example, ammonia is base, so water will act as an acid, right? This you have to remember, that acid donates H plus and base takes H plus. Base takes H plus. So what is happening here, that H plus has been transferred to ammonia because water is acting as an acid here. So this becomes what? NH4 plus, and because one hydrogen has been transferred to ammonia, so it will become OH minus. H2S is an acid, so particularly water can behave as a base. That means now the H2S will give hydrogen to water and it will form HS negative, and H2O will form H3O positive. So this is how you can remember the reactions. Amphoteric nature means that it can behave as an acid also and as a base also, depending upon the type of reagent that you are using with water. Autopyrolysis means what? That you will particularly learn in detail in ionic equilibrium. Ionic equilibrium involves this reaction at every step. So what happens here is that, let us say I am taking a water in the tub, right? So it will not have only one water molecule, it will have several water molecules here, right? So what happens here is that one molecule behaves as an acid and the other ones behave as a base. Now the acid one will particularly donate H plus to H2O and will form H3O plus, and itself it will be converted into OH minus. This reaction is known as autopyrolysis or self-ionization. Why it is known as ionization? Because here you can see that a positive charged ion, that is a cation, is being formed, and a negative charged ion, that is a anion, is being formed by the water. So water self dissociates into This is known as hydronium ion into hydronium ion, and this is known as hydroxide ion. Self dissociates into hydronium ion and hydroxide ions. Okay. Now, redox reactions involving water. What are redox reactions particularly? Redox, that means what? Reduction and oxidation taking place simultaneously. In one reaction, reduction will also take place and oxidation will also take place. So, what will happen here, that water on reacting with sodium, right? So, sodium particularly will gain OH and hydrogen gas will be released here. So, what is happening here, that here it is 0 oxidation state and here it is +1 oxidation state. So, basically what is happening, that sodium is being oxidized here. Sodium is being oxidized here and water is being reduced to hydrogen. Water is being reduced to hydrogen. So, because this reaction is particularly evolving hydrogen gas, that is why this water is said to be a great source of dihydrogen. That means you can synthesize dihydrogen, as we have already studied in the preparation of dihydrogen also. Now, next is water is oxidized to O2 during photosynthesis. That means if you reduce water, you will gain hydrogen. If you oxidize water, you will gain oxygen. This you have to remember. So, H2O will be converting into O2 and CO2 will be converted into C6H12O6 plus H2O. So, here what is happening, that in the reaction of photosynthesis, H2O is being converted into oxygen gas. That means it is being oxidized to oxygen gas. With fluorine also it is oxidized to O2. This reaction is very much important. This reaction is very much important. See, because fluorine is more electronegative than oxygen, what will happen, that fluorine wants to become F negative, right? Although oxygen is also electronegative, it wants to gain electron also, but here if you will see that because of the order FON, fluorine is electronegative, so it will like to gain electron. That means it will be likely to get reduced, right? So, it will particularly oxidize water to O2 and itself it will get reduced to F minus. So, particularly fluorine has the ability to oxidize water into O2. This reaction is of very much importance. Next is the hydrolysis reaction. This you will be dealing in the 12th class again, so pay attention to it. Basically, what is happening here, that you are hydrolyzing ionic compounds, right? So, for example, P4O10, you are treating it with water, it will get hydrolyzed to H3PO4, right? These reactions you will be also able to learn with a tricky way when we will do the redox chapter, right? When you will be able to calculate the oxidation state of the central element, you can see here, you can remember this, that phosphorus and phosphorus will have the same oxidation state here. This will be more clear to you when you will study the redox reaction chapter. So, what happens, that you can make a point here, that on hydrolysis, the oxidation state of main element does not change. Main element does not change. Right. So, P4O10 will form H3PO4 on hydrolysis, and the oxidation state of phosphorus in the reactant also and in the product also will remain the same. Then SiCl4 will be converting into SiO2 and N3 minus will be converting into NH3 on hydrolysis. Similarly, SO2 will be converting into H2SO3, calcium phosphide will be converting into calcium hydroxide, and calcium cyanamide will be converting into calcium carbonate plus ammonia. So, these reactions you can learn for now, but when we will study P block in class 12, then particularly you will understand the basic of hydrolysis, that how hydrolysis happens, then you will be able to particularly analyze these questions, these equations with efficiency, right? Next is the hydrates formation. So what is hydrate formation particularly? See, what happens is that association of water takes place. Here what is happening in hydrolysis? See, the reactant and the product are changing completely. For example, P4O10 is forming H3PO4, right? For example, let us take that if I hydrolyze copper sulfate, for example, this is a hypothetical reaction I am taking. If I hydrolyze copper sulfate, then it will be forming this. But if I am hydrating copper sulfate, that will yield you just 5 molecules of water associated with copper sulfate. So there is a difference between hydrolysis and hydrates. In hydrates, the chemical formula does not change, but some of these salts basically they absorb water and change their color like copper sulfate. But in hydrolysis, the whole compound changes into another compound. So you can remember this: chromium H2O6, barium chloride .2H2O and copper sulfate .5H2O. So the association of water particularly in the salts can be in 3 types: coordinated water, interstitial water and hydrogen bonded water. This we will learn that copper sulfate .5H2O, what is the structure. Interstitial water, what happens that let us take a structure of barium chloride. So in the voids of barium chloride structure, what will happen, that water will come and in the interstitial sites. Coordinated water, there is a whole chemistry that is known as coordination chemistry that you will learn in class 12. So you will learn that in detail, but for the timing you can say that water molecules form a coordinate bond that we have learnt in the chemical bonding with chromium. A coordinate bond is being formed, right? Amongst these, this one is very much important, that is copper sulfate .5H2O, right? That means copper sulfate crystal is associated with 5 water molecules. If it is associated with 5 water molecules, it will be in blue color. Now when you will keep it in sunlight, what will happen, that this 5 molecules of water will be removed, and therefore again the crystal of copper sulfate will turn into white crystals. That means if it is associated with water, if it is hydrated, then it will be of blue color, and if it is not hydrated, then it will be of white color. So here only let us explain the structure of copper sulfate .5H2O. What is the structure? See, what happens here is copper is associated with 4 water molecules. These 4 water molecules form a coordinate bond with copper, right? Now, 1 water molecule is associated with hydrogen bonding in sulfate. So this is particularly somewhat like this. Just a second, I am not having the space here. Yeah, copper associated with 4 water molecules here. Then through hydrogen bonding, 1 water molecule will be connected to sulfate, sulfur here. This is the structure. So this is 1 water molecule associated with hydrogen bonding to sulfate, and it is also forming hydrogen bonding to these water molecules, and copper is connected to only 4 water molecules. So a question can be asked from this particular structure of copper sulfate .5H2O. Now we will study about that what are deliquescent, what are efflorescent and what are hygroscopic substances. See, study these properly. Basically what happens here is that we get confused with hygroscopic and deliquescent substances. So pay attention to this. Substances are solids that absorb moisture from the atmosphere. Now this is very important. They absorb moisture from the atmosphere until they dissolve in the absorbed water and form solutions, right? What happens here is basically that they will absorb water from the atmosphere until they absorb the whole water and particularly form solution with it, right? For example, let us say that one substance is deliquescent, let us say A. So it will particularly absorb moisture until and unless it will be an aqueous solution by absorbing water vapor. That means it will be converted into a solution that is in the liquid form. Right, it will convert from solid to liquid or a solution particularly by absorbing water from the atmosphere. Next is hygroscopic. So hygroscopic substances also absorb water, but they don't form solution. They don't form solution. They can either absorb or adsorb. I have already explained the difference, that what is absorb and what is adsorb. Adsorb means on the surface it is sticking, and absorb means that it will present in the surface also and in the bulk also, right? So it can either adsorb also or absorb water also. It does not form a solution but absorb water vapor. It just only absorbs water vapor, but it does not forms a solution. Now comes the efflorescent solids. So substances are solids that can undergo spontaneous loss of water from hydrated salt. For example, let us say that A.H2O is a efflorescent solid. What will happen, that on a certain amount of heating it will lose water, and particularly we will obtain A, right? First it was A.H2O, then it was heating, it will be giving A plus water. That means basically it is removing water from itself, spontaneous loss of water from their hydrated salts. They do not absorb water vapor and they also do not form a solution. So these are the differences between deliquescent, efflorescent and hygroscopic solids. Example is NaOH is deliquescent. That means until and unless it forms a solution with water, right? That means it will convert into a liquid, particularly in a solution. It will absorb water from the moisture. Hygroscopic is Na2CO3, right? That means it will absorb water somehow, but it will not form a solution. Efflorescent is Na2SO4.10H2O, and this is known as borax. Na2B4O7.H2O. So basically it is 10H2O only, Na2B4O7.10H2O. So it also has the ability to remove water from itself. Now you tell me how many hydrogen bonded water molecules are associated in copper sulfate .5H2O. I have already told you the structure. Now you tell me how many hydrogen bonded water molecules are associated in copper sulfate .5H2O. Anyone? Again, if you will remember the structure, only one water molecule is associated with sulfate and forms hydrogen bonding. Other four molecules of water are coordinated. Can you see here? Again, I will tell you the structure. This is the structure. Four molecules of water are associated like this, and one forms hydrogen bonding. You can also remember this as copper H2O4 2 plus, SO4 2 negative, and water forms hydrogen bonding. So only one water molecule, that is situated outside the bracket, it is associated with hydrogen bonding. Now tell me about this question. Water is oxidized to oxygen by, this we have already done and I have emphasized on it also. Water is converted into oxygen by whom? ClO2, KMnO4, H2O2 or F2? Anyone? Water is oxidized to oxygen by, this we have done now only. Who has the special ability to oxidize water to oxygen? Anyone with the answer? Yes, very good, Ridhishri. The answer is F2. Good. So, F2 has the ability to oxidize water into oxygen and it itself gets reduced to F minus. Good. Option D. Which of the following is formed by the action of water on sodium peroxide? Water plus Na2O2 will give you what? Yes, Sudain, you are also correct with your answer. What should be the answer for this question? Water on reaction with Na2O2 will produce what? Hydrogen, oxygen, N2 or CO2? Okay. Sarayu, you are very much correct with your answer that oxygen will be produced. Good. So, Na2O2 on water produces NaOH plus half O2. That means oxygen gas is being produced. Good. Now, you have to complete the following reaction. First, you give answer for this, that calcium oxide on treatment with water will yield you what? I'll give you a idea that metal oxide plus water gives you metal hydroxide plus hydrogen gas. I'm giving you a hint. Metal oxide plus water will give you metal hydroxide plus hydrogen. Now you tell me that what is the formula of metal hydroxide in calcium oxide? If calcium oxide is treated with water, then what will be the product formed? This is a general reaction that metal oxide plus water will give you metal hydroxide plus hydrogen gas. Yes, Sarayu, you are very much correct with your answer that the answer for the first one is calcium hydroxide. Good. For the second one, see, for Na2 also it will be NaOH, but for Fe if you will take, it will be Fe3O4 plus hydrogen gas. That means this is a mixed oxide of iron. Mixed oxide of iron. Now, ferrous hydroxide or ferric hydroxide will not be formed here, rather Fe3O4 will be formed. Now, we will be doing hardness of water. So, particularly what is hard water and what is soft water? This topic is very much important. Sometimes while bathing, what happens is that the soap does not form lather, right? So, that is the condition for hard water. If the water is hard in nature, it does not form lather with the soap, and rather it forms into a white precipitate that is known as scum. While soft water, it forms rich lather with water. Rich lather with water. So, in this topic, we will learn that particularly what makes the water hard or what makes the water soft, and why does hard water does not form a scum. So, see here, This is a condition of the soft water particularly, that is giving a rich lather with water, right? So here the soap is giving a rich lather with water, that means it is a condition of soft water, because soft water has the ability to form lather with soap. So basically, if the soft water of particularly if the water is having salts like calcium hydrogen carbonate, magnesium hydrogen carbonate, or calcium chloride, or calcium sulfate, or magnesium chloride, or magnesium sulfate, that means calcium and magnesium in the form of hydrogen carbonate, chloride and sulfate, it makes the water hard. And hard water has the property that it does not give lather with soap, rather it leads to the formation of a white precipitate which sticks to our body, and it is known as scum, right? So water which is free from calcium and magnesium, it is called soft water, and that is why particularly it has the property to give lather with soap easily. So this is an example of soft water. See, hard water forms scum or precipitate. Why does it form scum or precipitate? Actually, soap, you are having this formula, right? In soap you are having sodium stearate, which reacts with hard water. So this is sodium stearate formula which reacts with hard water, and in hard water we are having calcium and magnesium. So this sodium stearate which is present in the soap reacts with calcium and magnesium which is present in hard water to give a PPT of calcium and magnesium stearate. That means this M can be calcium also and magnesium also. As this is insoluble in water, so basically a precipitate is formed here and it is of white color. So what happens if you are bathing with hard water particularly, it will form a scum like thing, that is this precipitate, right? And also if you will take boilers in geyser, right, in geysers we are having a rod, so if you are using hard water there, what happens that the white scum or the white precipitate of the calcium or magnesium stearate sticks to that rod, and therefore it will reduce the efficiency of the rod to be heated, right? Now the rod will be less heated because of this scum which has been stick to the rod of the geyser, right? So basically it reduces the efficiency of the boiler, and also it is unsuitable for laundry, right? Particularly that will stick to your clothes also if you will use hard water for the laundry. Now see the types of water, there are two types of hardness of water, that is temporary hardness and permanent hardness. Temporary hardness can be easily removed. For permanent hardness we have to follow down a procedure. So first we will take temporary hardness. Two methods are used, that is boiling and Clark's method. So if temporary hardness arises due to either calcium HCO3, calcium hydrogen carbonate, or magnesium HCO3. If the water contains these salts, that means that it is having temporary hardness, and it can be removed by two methods, that is boiling and the Clark's method. So boiling method, what happens here is that you will particularly heat the magnesium hydrogen carbonate. This will form magnesium hydroxide, and also if you will use heat the calcium hydrogen carbonate, it will be forming calcium carbonate. Now these are formed in the form of PPTs, right? So what will happen particularly, that let us say water is here and it is containing magnesium hydrogen carbonate. So when you boil the water, what happens that these magnesium hydroxide and calcium carbonate settle down as PPT. Now you can filter this water, right? And when you will filter this water, you can get the soft water. Clark's method, you add calcium hydroxide. So calcium hydroxide reacts with calcium hydrogen carbonate to form calcium carbonate. Again, it's a PPT. Or magnesium hydrogen carbonate reacts with calcium hydroxide to form calcium carbonate and magnesium hydroxide. Again, these PPT can be filtered out from your water, right? So two methods can be used. Either you boil the water which is having temporary hardness, or you can use the Clark's method, that means addition of calcium hydroxide, and then you filter out. Now answer this question. One of the following is an incorrect statement. Point it out. One of the One of the following is an incorrect statement, point it out. Which one is an incorrect statement? Permanent hardness can be removed by boiling water. Hardness of water affects soap consumption. Temporary hardness is due to bicarbonates, that is HCO3 of calcium and magnesium. Permanent hardness is due to the soluble sulfate, chloride and nitrates of calcium and magnesium. Anyone with the answer? A. Very good, Sudain. You are very much correct with the answer that permanent hardness cannot be removed by boiling water. Rather, temporary hardness can be removed by boiling water. Right? And hardness of water affects soap consumption. How? Particularly if the soap will not form a lather with the hard water. So, you will end up using more and more soap so that it can give lather. Yes, Ridhishri, you are also correct. Sarayu, you are also correct with the answer. Good. So, that's all for today. We will end up the session now and we will continue with the methods of removing permanent hardness in the next class. How can you remove the permanent hardness? Okay, so this topic we will be covering in the next session. So, that's all for today. Happy learning to all.